Okay, so the goal of this lecture is to spell out the details needed for defining the fundamental group. So let me remind you of a couple of definitions from last time. So we start with XP, a based space. So X is a space and P is a base point. And so we're interested in loops based at P. So this is a map with beginning and end point equal to the base point. A map from the unit square into X is called a homotopy between loops F0 and F1. Let's just call them loops. If so F at time I is equal to Fi for I equals 0 and 1, and F at F of 0t is P for all t, and that's also F of 1t. So the picture, one can picture a homotopy like this, where at the bottom, so this is the unit square, and the homotopy, so we label the square with parts, with what the map is restricted to that part. So the map on the bottom edge is F0, the map on the top edge is F1, and on the left and right sides, it's just P. That's what this condition says. And so the way we think about this pictorially is that we have two loops, F0 and F1. Maybe I want to draw this a little differently. Yeah, let me just draw it in this easy way. So here's F0, and then we have some other loop, F1, and this homotopy, so at each height, which is fixing a value of t, we get another loop. So this is a map of the interval that starts and begins at P. And these maps are what give us some interpolation between F0 and F1. Okay, so that's what the concept of homotopy means. So right, so let me tell you a couple of different ways to think about this. So if you write F sub t as the function whose second coordinate is t, so that's just what I was indicating here, the function restricted to height t. So this is a loop. And so varying t from 0 to 1, this gives us a path of loops. So this is a, so varying t gives a path of loops. Let me say it this way, a path in the space of loops. So the space of loops, that's all maps from the interval to X, which satisfy this base point condition. And then this is, homotopy is you can think of as a continuous path inside of that space. Yeah, from F naught to F1. Okay, so this is our notion of deforming loops. Okay, and so, right, so in this case, when we have this homotopy, we write, so this is kind of just a remark, and so then we write F naught is homotopic to F in this way. You say they're homotopic. Okay, so let me give some examples. So let's take X to be the plane. Y is going to be the plane without the origin. And Z is the plane without the origin and the point 0, 1. And let's pick base point, the point 1, 0. So first, let's look at loops in X. So any loop in X based at P is homotopic to a constant. Which we say is null homotopic in this case, homotopic. And you can see this via the straight line homotopy. Namely, we can take F of ST to be given by this formula. So when T is equal to 0, then this term vanishes and we're just left with F of S. When T is equal to 1, this term vanishes here and we're just left with P. And then when S is equal to 0, then this term is P here when S is 0. And so we have 1 minus T times P plus T times P is P. And similarly, when S is 1, we also get P. So, right, so this is, and if you fix, well, yeah, I mean, the way this homotopy works is, well, the picture is F, and you have P, and you have P and P here. And if you fix some S value, then this vertical line is doing the straight line, is mapped to the straight line between F of S and P, which is given by exactly this formula here. Okay, so let me not spell that out further. So that's why it's called the straight line homotopy. Okay, great. So now let's look at maps into Y. So let's consider G a loop in Y given by G of S is cosine 2 pi S sine 2 pi S. So it's just circle. So Y is, we remove the origin, and here's our base point P, and the image of this loop is just the unit circle. Now, in R2, this loop is null homotopic. It's homotopic to a constant, but G is not homotopic to a constant in Y. This is something we'll prove later. But for now, I just want to observe that the straight line homotopy doesn't work because, well, how does the straight line homotopy go. So every point follows the straight line back to P under this homotopy. And that's fine for almost every point except for this point here. The straight line goes through the origin. So at time 1/2 under this homotopy, we would have a loop that passes through the origin, which is not allowed if we're talking about a homotopy in Y. Okay. Okay, and then the last thing I wanted to point out is just that Z has many loops, which are distinct up to homotopy. So let me draw a picture to illustrate this. So Z is, we've removed 2 points, the origin and this point here. And well, okay, so there's lots of paths. We have something like the path we considered before. We could instead take paths around around this other point. We could take a path that goes around both of these points. Or there's even more complicated things that we could do. You know, we can, well, okay, so here's a picture. Well, you can go around here and then around there and back around the other way and so on. Okay. So recall that last time we defined pi1 of xp as the set of loops based at P up to this equivalence relation of homotopy. So we're going to denote brackets F as the equivalence class of F, of a loop F. So what we want to do is to make pi1 of x a group. And last time we defined an operation. So we have a function like this. Or maybe we didn't exactly define this last time. So what we do is the product of 2 homotopy classes we define as the homotopy class of the concatenation. So here, F concatenate G, this was the function given by, so we do F at twice the speed on the first half of the interval. And then we do G at twice the speed on the remaining, the second half of the interval. Okay, so right, so this is how the product is defined. So this is called the concatenation. And usually we'll write it, let me write it this way. So F product G is defined in this way. So, okay. Right, so there's something that we need to check at this point. So in general, when you define some function on equivalence classes, you need to check that it's well defined. That is to say, it doesn't depend on the choice of equivalence class. So we want to show if F1 is homotopic to F, and G1 is homotopic to G, then F1 concatenate G1 is homotopic to F concatenate G, so that this product is well defined. And well, so first let me draw a picture to convince you of this. So what we're given is we have a homotopy from F to F1, which looks like this. Maybe we call it capital F. And we also have the same for G and G1. And maybe we call that capital G. And we want a homotopy between the concatenation that first does F and G, and then between that map and the concatenation of F1 and G1. And there's kind of an obvious way to combine these two pictures sort of suggestively by just putting F here and G here. And that makes sense because, well, the place that these overlap on this edge, the map is constant, equal to P. So in a formula, the way this works, let me make some space. So in a formula, we will, okay, F, we maybe define, well, let's call it H, ST. So how do we do it? It's basically should be something like F concatenate G is what we want to do. At each time, that's what we should be doing. So it should be, yeah, let's try this. F of 2s, comma t, and then G of 2s minus 1, comma t. When, so here s is between 0 and 1/2, and here s is in 1/2, 1. So if you think in terms of the pictures, this is what you want to do. For every time t, you do the homotopy of f at that time at twice the speed, and then do the homotopy of g at twice the speed. Okay, great. So this shows that it's well defined. Yeah, I mean, you should check that this map does define a homotopy between these two, but indeed it does. Okay, and now comes the main theorem, which says that concatenation of homotopy classes satisfies the following properties. So for F, G, and H, any loops, and C, the constant loop at P, we have first, so we have three properties: associativity, identity, and inverses. So associativity says if we multiply F and G and H, then this is the same as multiplying F and G and H. doesn't matter how we parenthesize here. The identity says that if we do f and multiply with the constant loop, then this is f. And similarly, if we multiply with the constant on the other side. So the constant loop is playing the role of the inverse, and inverses, or sorry, the identity. And for inverses, so I need to explain what this f bar is. So this is saying inverses exist, and the inverse is given by the function that does f backwards. This is the reverse of f. Okay, so if f looks like this, then the reverse of f, well, it goes the other way. So let me draw it like that. This is f bar. Its image is the same, but it's traversed backwards. So as an immediate corollary of this theorem, we have that pi1 of xp is a group under concatenation. These properties are saying exactly that this product that we defined satisfies the axioms of a group, which insists that we have associativity, identity, element, and inverses for every element. That's what it means to be a group. Let me make another remark. So the theorem isn't true on the level of maps. We need to consider homotopy classes. So let me illustrate this. Like, for example, if we do f, it's not true that concatenating with the constant is equal to f, because, well, so f concatenate with the constant map at time s. What is this map? So it does f, and then it does the constant map. Right, so this is not the same as f in general. I mean, what does this do? This does f in half the time, and then it just waits at the point p. But in general, f might take the whole interval to reach p. Yeah, okay. So really, it is important that we are working with homotopy classes of maps in order to get this group structure. And as it will turn out, it's much more convenient to think about homotopy classes because, well, there's lots of loops based at a given point. I mean, if you have any loop based at some point, you can do a small perturbation of it and get another loop. And really what we're trying to capture is the fundamental features of a space. And so this kind of small homotopy, it doesn't really capture anything interesting about the space. So we don't really want to consider that loop as different from the one that I drew at first. Okay, so this is two reasons why we consider homotopy, because otherwise we don't have this group structure, but also homotopy is getting after the fundamental features of the space. All right, so now let's discuss the proof of the theorem. So I want to start with this identity. So the identity. So let's show, we'll just show, so I'm not going to give every single detail of every part. Let's show this statement. One also needs to show that C times F is F, but that will be similar. So let me first draw a picture to try to convince you why this is true. Well, what we want is a homotopy between F concatenate C and F. But C is, is just P for all time. But let me write C there. And well, so we want a continuous way to go from the map that just does F, just does F, and the map that does F really quickly and then just waits at P for some time. And the way to interpolate between these two is to do a map that does F, but then waits at P for shorter and shorter time periods. And one way to sort of draw this suggestively of what the homotopy should do is you wait at P for shorter and shorter time periods. So if you look at here, we're doing P for half the time. Here, we're doing P for, if we go halfway up, this should be like 1/4 of the time. And we do F correspondingly, all of F at the appropriate speed. Okay, so, well, we can write a formula for this. So let me first write down the formula for F concatenate C again, because this will help us figure out the formula for the homotopy. So F concatenate C evaluated on S. This is, so F of 2S, and then it's P. So, well, really what we want to do is to interpolate here with the speed. This is what's going to have to change. So at the one end of the homotopy, we want to be doing F at speed 1. So at the top here. And so T is gonna, so if we just consider 2 times T plus 1 minus T times 1, this map allows us to change the speed. So this, at time T is 0, we're just doing speed 1. Or maybe I want to do it the other way. Let me do 1 minus T here plus T times 1. So at time T is 0, we're doing speed 2, which is what we do at height 0 here. And then at time 1, we're doing speed 1. And this is a sort of a straight line linear interpolation between those two. So this quantity is 2 minus 2T plus T is 2 minus T. Does that seem right? 2 minus 2T, yeah, it seems okay. So what we're gonna do is F of ST is, so F, now the speed is 2 minus T times S, and then we do P. And the interval we do S on, or the interval we do this first part on goes from 0 to, so we want to get to the endpoint of F. So this quantity should be 1 at whatever endpoint we put here. So it should be, well, I guess 1 over 2 minus T. and then we should do P for the rest of the time. We can check that this sort of makes sense when, yeah, I mean, the speed here, well, yeah, I mean, the speed is now going from when T is 0, this is speed 2, and T is 1, this is speed 1. And yeah, okay, you can check that this homotopy does what we want. Okay, so this is the identity. This gives us the homotopy pictured here. And shows indeed that the constant map, its homotopy class gives the identity. Okay, great. Next, let's discuss the inverse. So what we want is a homotopy between F, concatenate F bar, and the constant map. So let's write down, well, yeah, so let me first draw a picture to show you what this is going to be. So, well, what is F bar? So we first do F, and then we do F in reverse. And, well, a homotopy, so we want to go from this map to a constant. Well, one thing we can do is just go along F for not quite as long, and then turn back. And this is okay because the map only has to be equal to P at the endpoints. So originally the map was also equal to P at time 1/2, but this isn't required for the homotopy. So as we go further and further along, we do F for shorter and shorter periods, and the end of F bar similarly. So okay, so this is what the function that we're going to define is going to do. So to write down a formula, let's first write down a formula for this concatenation. So by definition, this is F and then F bar to S minus 1. Okay. And now let's use the definition of the reverse. So this is not changing, but then F bar, so this is F at time, so it's 1 minus 2S minus 1, which is 2 minus 2S. So, okay, so this is the formula. So a picture of what this function on the inside here is, no, I want to do this function here. So this function is, so view this as a function of S defined on the interval. So first we do 2S. So here's, I mean, this is the unit square. So the first half, we do 2S, and then we do 2 minus 2S. So we go up and come down. And the homotopy is, well, at time, this is what we do at time 0, and at time 1, we're just going to be doing the constant 0 map, because then if we apply F to that, then that will just be the point P. And so in between, well, what we do is we just go up a little bit and we come down a little bit. So we go up to the point, this point is like 1/2 comma T, and then we come back down. So you can compute, so you can write down sort of a formula for these two lines, and that will tell you what to put in the homotopy. And so what you find is we should define F, capital F, as, so I've got here F of T, no, 2 TS. this 2t, that's giving the speed at time 1, at time 0, maybe I'm going, at time 0 it's 0, and at time 1 it's 2, the speed is 2. And then f of 2t 1 minus s. So we do this 0 to 1/2, and here 1/2 to 1. Okay, so you can check that this does exactly what we want. So like for time t equals 1/2, we do f of s just from s equals 0 to 1/2. So we only go halfway out along f, and then we turn back and come back. Okay, so this is what we want. Okay, and now there's one more thing, which is the associativity, which I'm not going to write down all the details for. Well, okay, in my notes I just say U, but let me give you a little more than that. So what we want, so let's think about what this means. F concatenate G concatenate H, and F concatenate G concatenate H. How do these differ? So in the one case, on the one hand, if you do F concatenate G concatenate H, so first you split the interval in two, and on the 1/2 you do H, and then you do F concatenate G here. But then doing F concatenate G here means you split that in two, and then you do F, and then you do G. And in this situation, first you split here and you do F and then G concatenate H, which is G and then H. Okay, so these are the two things you want to interpolate between. So on the one hand, you have F and G done at 4 times the speed over 1/4 of the interval, and then H done at twice the speed. And here you have F and then GH, where G and H are done at 4 times the speed. And well, the suggestive picture for the homotopy that we want between these is to, well, I mean, we just want to change the speeds of F and H actually. So G, it seems like we can keep its speed the same since it's going at 4 times its usual speed in both of these concatenations. And you can do that in sort of a straight line way, the same way we did the other ones. So, okay, I'll let you write down the details there. But given that, then this completes the proof. Okay, so I think we'll stop there, and next week the goal will be to do some computations rigorously.